Thank you. I'm back again with a different topic. This time we are going to discuss about the commit synchronization in Postgres. Because very frequently we come across tuning this and convincing many of our customers to improve the performance. Yeah, so I thought of talking about this. And yeah, so overall, the presentation is all about the durability of asset rules and how Postgres is going to handle that. And today's the talk agenda is the big picture of entire DML operations. I'm not going to go in deep, only the peripheral things. And why the WAL. WAL stands for write ahead logging. And that's where the durability is assured. And what is WAL and what it is called, what is the WAL segment, and the WAL records types, and we are going to see some of the internals, how the system works. And finally, we are going to look at some of the parameters, tunings, and its implications. Okay, so let's get started. So the complete picture will be very complex for a DML operation. The blocks need to be fetched from the disk to the memory, and if required, new pages will be added, and the WAL records will be prepared, and it will be there in the WAL buffer, of course. And finally, it will be flushed to the disk. The WAL will be written and the commit and acknowledged to the client. And at the same time, the blocks which are getting dirtied in the memory by all this transaction will be written to a disk, but that goes in asynchronous fashion. And finally, the checkpoints will be happening. So there are multiple Postgres process involved, the checkpointer and background writer. At the same time, there are dedicated process which deals with the WAL part only, the WAL writer and WAL sender. And at the same time, there will be WAL receiver at the standby side. So today, this presentation is all about the WAL part of this, because we cannot deal with the entire picture. Yeah. So this to give the overview. So we are going to see only that box part, the red box. So why WAL? Oh, the answer is very simple. The memory, the RAM is volatile. Anything you write to RAM, if the server crashes, it will be lost. Very simple. And durability of transaction need to be assured by a database. So if you look at the Wikipedia definition of durability, it guarantees that transactions have committed will survive permanently, whatever happens. So that's what expected from a database. So that's where the WAL comes into picture. And so even in the, currently in the chat, there were many questions about high availability and all. So this is how the overall journey about the WAL. So all high availability is all about durability. The data you committed should be available always and should not be lost. So any Postgres high availability solution will look like this from top. So application will be writing to the primary, and the primary will be writing that into its Postgres data files asynchronously, and most importantly, the PG, the WAL file. The WAL files will be the primary place where the data transaction will get committed. And it won't be staying there. If it is staying there, if that disk crashes, you are going to lose the data. So we need to have some external mechanism. That's where we take that to archive destination or stream it to standbys. So the high availability or the durability altogether is all about the journey of WALs from the primary till the standby or the backup or wherever. Yeah. So at the very basic part in the previous screen, we can see that the WALs is getting archived. So if there is no archiving happens in your system, please do it immediately, because that is ensuring the second level of protection for your transaction. So always the WAL should be archived. So those who are coming from Oracle background, it will be clear because redo need to be archived. So that happens with other database systems as well. And this WAL archive will serve three purposes. It's part of the backup, and it is mandatory for point in recovery, and all the standbys may need it in addition to streaming it. So if something happens to the continuous streaming of WAL to the standby should be able to get it from the WAL archive. Okay, so basically there is two parameters which is controlling the archive mode, which tells Postgres please archive the WALs, and there is archive command which can execute any custom scripts and the commands. So this is the basics, the very basics of the WAL. So we are getting little more into the WAL. This is a common confusion point for many users who comes to the Postgres for the first time. In many database systems, we have the redo groups, and it works like a cyclic fashion. Okay, rise to the first redo. Once it is filled, go to the second one, then third one, again go to the first one. So we have many database systems doing that. But in Postgres, we don't have the cyclic WAL, the redo. We have a linear the WAL record. So it is address space of 8 bytes. 8 bytes means it is going to be 16 exabytes. So normally you are going in lifetime, you are not going to exceed that. So that's a astronomical big number. And each record in the WAL is identified by LSN. It's a logical sequence number, and it is 64-bit. So it's ever growing number. And so as we see, since it's a continuous address space, the system may find it difficult to handle. So there is some logical way of dividing it. So we generally divide that into segments. So by default, we have a 16 MB size, the WAL segments. So we need to understand it is not the real WAL. It's only a part of the WAL. It's a segment of WAL, and we are logically dividing it into segments. So and we can do it even if it is 16 MB by default. From Postgres 11 onwards, we can change it using the WAL segment size at the time of initialization. If there is a lot of if it's a heavy system with a lot of transaction happening, we would recommend changing that to a bigger value, 512 or a bigger one. Yeah, and we have many customers doing that, and they are getting direct and indirect benefits out of that. Okay, and yeah, and these big segments contains the WAL records, the LSN which we mentioned earlier. Those are the actual records. And when we see the first the diagram, we saw that first the WAL records are written or created in the WAL buffers. That's a place of birth of the WAL, and then it will be moved to the WAL segments. Okay, and for any crash happening at the Postgres level, the WAL replay starts from something called redo point, which is associated with the previous checkpoint. The last checkpoint will have a redo point. From there, all the WALs will be replayed, and there is some smart mechanism by which many of these redos can be skipped, because we'll see that. And okay, so the WAL contains the WAL records. The WAL segment contains WAL records, and each record is related to one change in the one type of transaction, one type of change in the system. So, and it has a header associated with that. And each of those header defines a resource manager. We'll see later on what type of record it is. And there is Postgres does something called full page writes. So the WAL records can be a full page writes or regular WAL records. The full page writes happens to recover from to ensure the recoverability of the database. So if after the checkpoint, if the page is getting modified for the first time, then the full page will be written into the WAL, so that after the checkpoint, we have the confirmation that we can recover the database, all the changes. The full page is available in the WAL. And since we have multiple types of WAL records, there was confusion initially because the Postgres source was getting complicated, and we standardized that WAL record format in Postgres 9.5. So the code is much more cleaner and things like that. And this is so I was doing some compiling of all types of the WAL records. So these are the types of WAL records. It's a big list. No need to go in detail. But at the end, we can see that there is something called generic WAL records. So this is the beauty of Postgres. Postgres is extensible. We can add custom indexes and things like that into Postgres, which can produce a generic WAL record, and it can be transmitted to standby. So the real meaning of open source, you can modify the Postgres the way you want if you have the code level expertise. And the last one, the logical records, which records additional information in the WAL for decoding, for the logical decoding. This is part of the Postgres, the logical replication. Yeah. And yeah, so obviously the question comes, what type of information gets recorded into the WAL? By default, the WAL level is set to the replica, means the Postgres writes enough information to the WALs for a recovery, for an archive recovery. You can take a backup or archive and recover the database. So that WAL contains sufficient information to do that. But there is a minimal, we can set the value to minimal, so that Postgres will do very minimal WAL logging, that to just support a crash recovery. That's a bare minimal WAL level. And in the opposite side, we can change it to the logical, which adds a lot more extra information, so that logical decoding can be supported. So we have the control what need to be written to the, how much data need to be written to the WAL. Based on the requirement, we can change it. And so since we are talking about the commit and the transaction, this is the overall control flow happens in Postgres. First, there is an entry to PG exact. The commit log entry will be made to. So PG exact is just an example. There is a multi-transaction and sub-transaction. Postgres has a lot more complexity to handle. This is very generic, the bare minimum transaction, where the entry goes to the PG exact. That records what type of that initiate the transaction record. Okay, it's so it's called commit log. It is a 8K page, and the PG exact is the directory where this will be written. And basically it's a memory area, 8K page, and it's a continuous array. Data will be stored in that array, mentioning that what are the transactions. So looking at this, we can, the Postgres can say what are the transactions in progress and how many are committed, completed. Yeah. Once this commit log entry is made, the Postgres modifies the pages, we call heap pages. It will be modified, and corresponding WAL records will be generated. and the WAL records will be in the WAL buffer. And here you can see it updates the page, the heap page with the LSN. Okay, because the heap page records the LSN, and that can be utilized for crash recovery, because Postgres need to know from where the crash recovery need to start. So if the page contains a LSN number which is higher than the LSN in the WAL, those records can be skipped because the page contains the latest information. So the Postgres can speed up the recovery. And as we discussed, Postgres does continuous background writing and checkpointer. So generally, most of the information from the last checkpoint till almost near the crash will be there there is a higher chance of that recorded in the pages. So the crash recovery can speed up. Yeah, and if the transaction commits, the WAL commit record will be written into the WAL, and of course there is a flush happens. That's how the durability is ensured. Flush the WAL buffer, and once the transaction is committed, then go back to the commit log and change to status from incommitted to commit, in progress to committed. This is the overall control flow happens in Postgres. And when it comes to what type of synchronization happens with the disk, first of all, the flush, the fsync call happens only if the parameter fsync is on, and we must make sure that it is on in Postgres. Otherwise, you may end up in corruption. And unfortunately, there are a lot of materials online and people recommending to turn fsync off, which is a way to tell say, please corrupt my database. So never do that. Fsync must be on. And the synchronization, what are the types of synchronization? Flush, the fsync, the OS can support. All these things can be selected from the Postgres as parameter. The parameter name is WAL sync method. In Linux systems, the default is the second one, fdatasync, which means write the flush only those data and the basic metadata about that change into the file system. So instead of completely flushing the entire metadata of the file, the inode, and there are a lot of metadata about the file, the change, access time, modified time, change time. No need to write everything. Only those if extra pages are inserted, okay, those pages and the reference to those pages. The very basic things. So fdatasync is the default in Linux, which can speed up the things. And we have a lot more options. The default fsync is there, and fsync right through the disk cache, and the system call like direct open also available in Postgres. So the user has the ability to choose, but the default is good enough. But please understand that it does the minimal and optimal writing. And in general, the Postgres does a lot of buffered I/O. The buffers, the blocks are modified in memory, and it is written into the cache. The kernel, it can be the OS cache or write back cache, or at library levels, libc level, we have caching. So the background writing or the checkpoint writing goes through all this cached writing. So, but when it comes to WAL, it cannot afford to have all this caching. So it need to do more direct kind of writing. But the storage write cache may exist there, but if it is not battery backed cache, better avoid that using a write through. It need to be really almost direct writing. But again, coming back to the direct IO, Postgres has WAL direct IO option, but it won't be doing in general case because the WAL records are further required to be propagated to the standbys and archives. So if it is direct IO, again, it will result in reading the same thing again. If it is available in the OS cache, it's or somewhere, it is easy to read and it speeds up the things. Yeah, so this is a little more internal. So the WAL record preparation, everything starts with this internal function. Since the data need to be written into the WAL segments, so many sessions, so many concurrent sessions updating that WAL segment will be a problem. So it is protected by locking methods, locks. By default, the xlog insert lock is set to 8. There is a lot of discussion but it is not user changeable. And in the community, there is an agreement that this works best for most of the users. But in case you need to change for your extreme machines, you may have to change this at the code level. But currently, we don't have any other option than so. The logs are required to get the position. Okay, as you can see, there is the entire process is two-step process. First step is reserve the right amount of space in the WAL and then copy the record. So if there are multiple processes are involved, everything should not clash. So the reservation of the space and things need to be protected by the logs. So there is 8 logs by default. And of course, there is if there are more logs, the overhead is more to find out. There is some optimizations done. If the same process is going to take a log again, it will try to acquire the same log which was used previously, so that it don't have to scan through all the available logs. So there are a few optimizations in the code. So lesser the log, the overhead is less, but yeah, there could be some level of contention at the extreme load conditions. Okay, and finally the xlog flush. So the fsync supports, as we saw, there is a multiple flushing methods, and always make sure that the fsync is on. I repeatedly saying that because it can lead to corruption. And the WAL, once it is committed to the WAL segment, the journey is not ending there, as we discussed. This is a part of the finishing segment. I just took this code to explain what are the further steps happens. The WAL sender wake up request. It's basically telling that, okay, the WAL sender to get up and you have something to do with there is some work came. And then it need to notify the archiver process using a notification. And optionally, there is in special conditions we need to do the checkpoint also. So the WAL sender and archiver are asynchronous. So because they will be lagging. If the archiving is happening to some, for example, cloud bucket, it could be slow. So it could be lagging behind the WAL generation. So it may take some time. So asynchronously, it need to be notified. There is some work came. And Postgres does it, this notification using a mechanism called it's basically creates a file, .ready file in a directory in pgval. So the archiver can come and look into this name of the .ready file and understand what are the WAL segments it need to be archived. And once it is archived, it will change the name from .ready to .done. So it's a it may appear as very crude method, but it really works wonderful. This is an asynchronous way of communicating with the archiver. And as I mentioned, the archiver can be any custom script as well. And the WAL Senders, of course, WAL Senders basically tells to wake up, and it basically reads from the disk on the primary side. And each WAL Sender will be sending that information to one recipient. And it works like normal Postgres connection. When a WAL receiver connects, the WAL sender one WAL sender starts, and it sends the WAL records over that. Instead of replying to normal connections, will be replying to queries. Instead of that, the WAL sender will be sending the WAL records. And so as I mentioned, why the direct IO is avoided, because it need to again read from the disk. It could be it may lag, and if there is a cache, it will speed up the things. So this is one thing which very interesting for many of the users. Postgres supports asynchronous commit. Okay, basically it tells that the reply the commit back to the client without actually writing, without flushing to the disk. Okay, which is against the concept of durability itself. Postgres comes back and tells, okay, it's committed, but we can utilize it for optimizing a lot of areas. For example, if it's a banking transaction or very critical part of the transaction, we need to ensure that, okay, it is committed and coming back, really return to the disk. But if it's some kind of logging or auditing, or there are a lot of things happens in the data. So there is a bulk data loading. We discussed about the migration. So many of those things, in a system, 75% of the workload may not require a synchronous commit. The commit can happen immediately after some time. The Postgres can acknowledge back the client that, okay, proceed. So Postgres provides to control these even at the session level and even in the transaction level. So if I have a block of statements, say do the transaction, okay, which need to be doing synchronous commit, then all the logging and auditing, okay, this transaction happened to some other, that need not be happening in a synchronous fashion. So only that main critical transaction portion can be doing a synchronous commit. It can be the statement is set local. Set local means within the transaction. So once the transaction commits, it will be asynchronous again. So those people who want to take the maximum out of the performance from the servers, they can tune this to the best level, catering to their requirement. Unlike fsync. So as I mentioned, fsync, if you turn it off, you may be corrupting the database, but you can safely turn off synchronous commit. This won't be affecting the integrity of the entire database. So it means it won't get corrupt. But the last few of this transaction might be lost. If it is not critical, you can, if you are afford to have it, yeah, this can be done. It can be set at the user level, or at database level, or at session level. Yeah. And there is these parameters has some implications. So by default, the synchronous commit will be on, and which means if there is a synchronous standby, that WAL record will be returned to the standby. The primary can send the WAL record to the standby and getting an acknowledgement that it is returned there, but it is still wait for the flush also to happen if it is on. And if it is apply, the primary transaction will wait for the remote write, flush, and apply the transaction there, so that the same information will be available to the standby or any user connecting to standby. And the third one, the remote write, which is the best in many cases, where we need to ensure that the WAL records are available in the standby side. So it will just do a remote write. The flushing and apply may happen later on. So a lot more speed up can happen. And the other option is local. Local means do only local commit. Yeah. So these are the areas where the fine tuning based on the requirement can happen. Yeah, and going to the last slide. Yeah, and this is another obvious question. So, okay, if you are turning off the synchronous commit, how much of data you are going to lose? Okay, the answer is this: last 200 milliseconds data, because there is a WAL writer delay, which is the default value is 200 milliseconds. The WAL writer will be writing in every 200 milliseconds for sure. So it will be written. Or at 1 MB size, if the system is generating 1 MB WAL, it will be definitely written. So if there is a asynchronous commit, not synchronous commit, the maximum data loss will be this much. But in a heavy system, in a very high transaction system, you may lose data up to 3 times of this WAL writer delay, because there is optimization in the WAL writer to write a bigger page. Yeah. Otherwise, it's 200 milliseconds is what I lose. And this is a commit delay and commit siblings. So unlike the asynchronous commit, this will ensure that the data is persistent, but it delays the commit so that it can commit lot more parallel things at a time. So if there are 10 sessions and they created 100 WAL records, and all those things can be committed at a time. So all the clients may experience a slight delay, which can be controlled by this commit delay, but it will get acknowledgement only if it is committed. So it's a balance. This also can be tweaked. And the common mistakes. We see that many places the WAL archiving is not happening. It is not turned off, and surprises happens, and data is not recovered. Please make sure that the WAL archiving is happening. It is part of the durability, and fsync should not be off. Fsync must be on. Please make sure that it is on. Otherwise, database may corrupt. And the consumer grade storage. In the community, there is a lot of discussion about this because many storage acknowledge back that it's written actually without actually writing. So, but in reality, I didn't encountered much of these issues. But the fourth one, the virtualization impact, that's a lot of people get into this problem. There are well-known virtualization solutions which won't actually give the 8K page properly to the underlying host operating system. Instead of that, it will only give the 4 KB first. And if that server crashes at this time, the page will be tiered. Corruptions happens. Yeah, it's reported widely. And the last one, the WAL log hints. Preferably make it on because many of the rollback, the PG rewind kind of things request this. Especially people were asking in the chat that how PostgreSQL works. So PostgreSQL requests joining the node back to the cluster again after a crash. So the rewind should happen. So enabling the WAL hints or enabling the checksum will indirectly make it on. So enable the checksum so that the corruptions can be avoided, as well as the WAL hints will be, the hint bits will be WAL logged. Okay, and some good references. Yeah, that's all from, hope this is interesting, at least something take away.